All right, so now it's time to learn how neural networks learn. In this section, we will learn about two of the main processes that help or actually make neural networks learn, and those are called backpropagation and gradient descent. They work together to update the parameters of a network so that it will be able to capture the pattern that is in the data. In this lesson, I will first give you a more intuitive example or explanation, and then I will go into the details of how it works in a more mathematical way. So let's start with this simple network. Let's say we have a bunch of data points, and in all of these data points, we have two features. That's why we have two input neurons, and the output of the network is going to be one number. Let's say we give our first input to the network, and then we get an output, right? As you know, when we are first starting, of course, the network is initialized randomly. The weights and biases are initialized randomly. Then again, weights are initialized randomly. Biases are most of the time initialized to 0. And then with everything, what we've seen in the previous lesson, we are able to calculate the outcome of the network. And then, of course, there is the actual outcome that we are going to try to capture. And then we give the second example or second data point. We get an output and we also have the actual value, and same with the third example. So what happens from this point on, let's say we only have these 3 examples so far, is that we see the error that we made. So this error could be too high for some of the examples, could be a little bit lower on the other examples. But the main goal from now on is, based on this error, how can we update the weights and biases of this network so that we will have less of an error next time on the next run of the network. So let's see what our errors are. We were able to get really close with this last example that we fed into the network. The previous ones, we actually made pretty big errors. Let's say the output is supposed to be from 0 to 1. So if you're making a 0.86 error, then you can think of it as a big error, of course. What the network does from this point on is to see how much it's supposed to change each of the outcomes to be able to capture the actual value, to lower the error. So we see with the first examples, we need it to be a little bit higher. For the second example, we need it to be a lot higher. For the third example, we actually need it to be a lot lower. So from this point on, the backpropagation kicks in. What it does is, it checks for each of the biases of the neurons that we have, and also each of the neurons in the network, how they are contributing to the error that we have. So I'll say that again. In backpropagation, the goal is for each of the weights and each of the biases, and if there are other parameters also, then we will also include them. So for each parameter, the backpropagation calculates how much and in what way they are contributing to the error or the cause or the loss. And once we have this information, what we have is basically kind of like a graph, right? So we will have it for each of the parameters. We will probably have them in one big graph also. But if, let's say, we only had one parameter, so let's say we're only talking about the parameter of this one neuron, then we will have a graph in front of us that shows us, based on how much I change the parameter, how much the error will change. So if it looks as simple as that, that means if I move 1 unit to the right, the error will go from here to here, so it will get a little bit higher. If I'm here, like let's say this is the point where we are, then it means if I move to the left, then the error is going to be this much lower. So this is what backpropagation does. It calculates the relationship between the parameters and the error. Once we have this information, gradient descent decides which way to lower these parameters. So if it's a 1-parameter system, like in this example, it's going to be very simple, right? And if it's also like a very simple graph like this, yes, error, we want it to be lower. If the error is here, and to make it lower, where should the parameter go? Well, it's supposed to go lower, right? So it's supposed to go this way. So we know that it should go this way. And every time by calculating the slope of this line where the the line touches the point where we're at, we know in which direction to go. And by this, we can get lower and lower and lower. And how further we go in all of these steps is determined by the learning rate. So as you saw, we jumped from this point to this point to this point to this point, right? You can also make the learning rate lower so that this jumping would be a shorter jump. So basically all of these jumps would be shorter at the end. You can also make your learning rate very high, then you might maybe jump from here all the way to here. We will talk about the implications of having a very high or low learning rate. But for now, all you need to know is that learning rate determines how far we jump while we're doing the gradient descent step. So you might say, okay, you know, this looks quite simple. Why would we even need a complicated system to calculate which way to go? If we have a graph and if we know which way to go, then we can easily take a step towards that direction. But that doesn't happen that way most of the time. It's because we have complex graphs like this one, for example. But on top of that, even here, as you can see, we only represent 2 of the parameters against the error. Whereas even only in this system, we have tens of parameters that contribute to the error somehow. And we cannot even show it in a graph anymore, right? Because that's going to be like 20-dimensional surface or space where all of the parameters affect where the error goes. So that's why we need gradient descent. That's why first we do backpropagation to understand their effect. That's why we have the gradient descent step to decide in which way to change all of these parameters. So this was the intuitive explanation of what happens, but let's look under the hood and really understand what's going on. And for that one, I'm going to dive more into the math, but don't be scared. I think it's going to be very clear for you after you listen to the next section. So for the sake of the example, let's say we have a very, very, very simple neural network. It only has one input neuron, it has one hidden layer with one neuron only, and it has one output neuron. And when you want to do what I'm going to show you in a second with a bigger network, what's going to happen is that you're just going to do the same calculations over and over again to calculate it for a whole layer with more neurons or for more layers. A bunch of things that I want to point out. As you can see, the first connection has the weight 1. The second connection has the weight 2. My neurons have biases. And extra things you see here is A's, right? So these A's are basically the output of a certain layer. In this case, a neuron also, but a certain layer. These are calculated after, so A's determine the outcome after, or point out the outcome after we put the outcome of the layer to the activation function. So if you remember, we had a Z that has that's only the output of a layer right after you calculated with the weight and bias, and when you put in an activation function, then we have the A. That's kind of a notation that's commonly used out there, and I just want to mention it here and there in this course so that you're familiar with it also. And you can see that we have these numbers in little brackets that are on top of the symbols and not below them like these ones. And this determines the layer that it belongs to. So this belongs to A1 belongs to the first layer. So that is the outcome of the first layer. A2 is the outcome of the whole system, effectively the second layer, basically. For input, I'm going to use A0 just to have a consistent notation so I don't have to write it separately for X1, so don't get confused there. All right, so what is the true value of this network? Let's say the true value is Y. How would I calculate the cost then, like we did in the first example in this lesson? If the true value is Y, then the cost is going to be Y minus the outcome of the network. Many times you will have a little bit more of a complex way of calculating the error or the cost, but just for the sake of simplicity, let's just say that the way we calculate cost is by subtracting the predicted value from the actual value. All right, so let's start creating a dependency tree to understand what C depends on. So looking at this example, C depends on Y, which is a true value, and A2, which is a predicted value by the network. Next step is A, right? As I said, A here again, make sure that you understand that this is the A, this is the outcome of the network, and this is alpha, which is the activation function. So A, the outcome of the network, depends on Z, which is just the outcome that we calculate using the weight and the bias. As you can see in the next step also, Z is calculated by multiplying the outcome, the input that comes from the previous layer, by multiplying it with the weight and by adding it the bias. So it happens here, and after we put it in the activation function, then we get the outcome of that layer. And we just keep adding it to our tree. Z depends on the weight, the bias, and the outcome from the previous layer. And again, we have the same thing. The outcome of the first layer depends on Z, and Z depends on the weight from the previous layer, the input itself, and the bias. So from this point on, what we want to see is how changing any of these parameters in this tree would affect the cost that we're getting at the end. So basically, I want to see if I change this by 2 units, what will happen to the cost? If I change this by, or lower it by 2 units, 5 units, what will happen to the cost? And luckily, there's a nice and neat way of doing that, and that's called getting the partial derivative of something. So what we're going to do to understand the relationship between all the parameters and the cost is by calculating the derivative of the cost with respect to all the other parameters. So this is what it looks like. This is what we say the derivative of the cost in terms of, or with respect to a certain parameter. These little things that look like a D is basically the derivative. And this notation tells us the partial derivative of C with respect to the weight 2. How you do this is basically by using something called the chain rule. So as you can see here, this is kind of looks like simple math, right? So just don't get confused by all the derivatives, but you can see, so we want the derivative of the C with respect to V2, the weight 2. What we do is then we can get the, because we know weight 2 is dependent on Z2, we can get the derivative of Z2 with respect to W2, the weight 2, and then we can get the derivative of A2 with respect to Z2. We're basically following the tree further down to the cost, and then we can get the derivative of the cost with respect to A2. So there's a little typo here. This is supposed to be a capital C, but just so you know. And as you can see in this like basic math way, if you see that these cancel each other out, these Z's, derivative of Z, and derivative of A, the outcome of the second layer, just cancel each other out. And at the end, we have derivative of cost with respect to the derivative of weight 2. So that's why we can kind of expand this to make it easier to calculate, because this is a value that is not accessible to us. We're not aware of what this would be. That's why we divide it into smaller chunks and calculate this one because they're closer and we know how they relate to each other, and then this one because they're closer and we know how they relate to each other, and then this one, so that at the end we are able to get a value that tells us how the cost changes every time we change the weight 2. So what happens is, from this point on, we calculate this value by using all the data points or all the examples that are in our data set, and then we average it. And once we average it, we put them all in a big vector where if we have all the derivatives of the cost with respect to all the parameters that are in our network. And this is called gradient vector. And gradient vector is the thing that tells us how all the parameters relate to the cost. Once we have this vector, now we are able to update the weights and biases to the parameters of the network. So how that happens is, let's say we still have our nice little network, right? And the parameters that we have here are the weight, 1 bias 1, weight 2, and bias 2. So we want to know how to update these ones. And we also have the gradient vector. So we know how weight 1 contributes to the cost. We know how bias 1 contributes to the cost, and so on and so forth. So what we do in gradient descent is basically we just subtract the two vectors from each other. So at the end, we have the updated values for the parameters. This is a very simple way of doing it, of course, but there are more complicated and more sophisticated ways of doing gradient descent. We will talk more about them when we are talking about how to deal with the computational time or computational cost that comes with training neural networks or training deep learning models. So we will go into more details on this and see how they are calculated also. For now, this is all we need to know about gradient descent. And with that, we are ready for our exercise. What we're going to do in this first exercise is to build a very simple neural network using Keras. So hope this was all clear. If you have any questions, do not hesitate to leave a comment or send me an email to ask them. But it will be even better if you leave a comment so everyone can see your questions. And with that, I'm very excited. Let's get to the exercise.